Hello, and welcome to Regenerative Restorative Dentistry, the quest to heal and seal, or as a friend has called it, Restorative Dentistry, the next regeneration. I'm Dr. John Comisi, and I live and work in Ithaca, New York. I practice comprehensive general dentistry, and I'm always on the lookout for ways to improve the way that I care for my patients, which is why I'm here with you today. I've had the pleasure of writing and lecturing on this subject for quite a few years now. And if you're interested in reviewing my publications or finding where I'll be speaking next, please take a look at my lecture website, thepracticaldentist.com. You can also email me at jcomisi@jcomisi.com. For geographic reference, I present to you this map. Ithaca, New York is a wonderful college community in central New York, indicated by the A on the map. We're about 4 hours northwest of New York City, an hour south of Syracuse, New York, and about 3 hours east of Buffalo, New York. Our community has been called centrally isolated, but I have sincerely enjoyed living here for more than 33 years. In July of this year, this article was published in Dentistry Today and is the basis for this webinar. I invite you to take the time to review it after this presentation and then share your comments with me. I'll be exploring my thoughts on this subject at the American Society for Dental Aesthetics meeting in a workshop given this coming October. And again, I invite you to join me in Miami, Florida at this wonderful meeting. I have for the past several months been contributing to the Dental Biomaterials Science and Research Group, dentalbmsr.org, founded by Dr. Salvatore Saro. He and many others, like Liviu Steyer and Yuma Daoud, have posted and contributed incredible information for the growth of my mind and so many others, and I invite you to join this group and participate on their Facebook page. Everyone can join. Just request membership. We now have almost 10,500 participants in the discussions on the Facebook page and the online learning community. I was invited to participate in this summer school in Finland earlier this year and was the only U.S. practicing dentist to attend. It was a remarkable experience, and again, by participating with this incredible group of brilliant researchers in the dental materials and dentistry, I learned so much from them, much of which I will share with you in this presentation. So let's get started. Resin adhesive bonding has become a standard practice in the U.S. and around the world, and composite restorations have now become the norm. And yet, numerous research studies are starting to call into question the effectiveness and benefit of resin adhesive bonding. This paper from the journal Dental Research in 2014 calls our attention to a few things. First, the title, Proteins, Pathogens, and Failure at the Composite Tooth Interface. This paper has a call to action, the need to find, quote, innovative strategies to mitigate the pathogenic effects and slow deterioration, unquote, of our composite restorations. Second, it calls out the fact that the fracture rate of composite restoration is nearly double that, the failure rate, of composite restorations is nearly double that of amalgam. And lastly, quote, the increasing trend to replace amalgam with composite could be detrimental to our patients, unquote. The previous paper is not alone. Many other papers are calling this to our attention, such as this systematic review and meta-analysis. Why is this occurring? Well, I believe we need to go back to the basic science of it all. I did not know Arzu Tesvergil Mutlue when I read this article many years ago, but having had the chance to meet her in Finland was a great honor. This article was very important when I read it and probably started me on my quest to learn how to improve our composite restorative procedures. What amazed me is that the NIDCR comment on the composite failure rates of being 5.7 years. Why is it not being looked at more seriously by the practicing dental community or by the dental industry? This fact is very disconcerting to me, and it should be to you as well. Going back to Jack Ferricane's article previously mentioned, it is interesting to see that he points out that although the failure rates have been known for many years, current research and development in the industry has mainly been focusing on resin and filler modifications, and that the number one failure of composite restorations is recurrent decay. Secondary reason is fracture. And interestingly, he states that the most popular current formulations are weaker and less fracture resistant than those sold in the 70s and 80s. Which leads to this type of situation, catastrophic failure of our composite restorations. The University of Oregon has shown that biofilm accumulates on composites and the margins. As the margins open, a gap forms from the washing away of the bonding agent. The biofilm is then drawn into the gaps and eventually all the way down the spaces between the composite and the enamel and dentin. As the biofilm progresses, demineralization of the enamel and dentin margin occurs. These result in extraordinary leakage. Clinically, we see this every day. We must find a way to stop this progression. We have over the years encountered numerous bonding generations and systems, all with the intent of removing the smear layer from the restorative interface and create hybrid layers. But why are there so many generations? Well, first of all, teeth are alive, constantly responding to the environmental factors that they encounter every time we eat, drink, and breathe. Over the years, of course, we have found that bonding to enamel is easy and has long-term predictable results. However, bonding to dentin is difficult at best because dentin is very, very different than enamel. Chow and Vogel described one of these challenges we encounter when attempting to bond to dentin. First, the tooth, including the enamel, is a semi-permeable membrane, dealing with the environmental effects of acids on a regular basis. So, as it demineralizes, the tooth remineralizes it via a mechanism of delivering calcium and phosphates to the affected area and attempting to remineralize that area. Second, these ions have to come from somewhere. Yes, oral saliva is one source, but interestingly, as they point out, they also come from within the tooth via the dentin fluid flow. So there's a constant fluid flow from within the tooth outward. Odontoblasts are defensive. They are the first line of defense of the tooth. Once they detect bacteria, they're going to react to the acid attack. In fact, any acid attack. The odontoblasts have no way of differentiating where the acid is coming from, whether it's from the bacteria or from our restorative process. It just knows that the dentin is being attacked by an acid and reacts secreting matrix metalloproteinases, cytokines, and other defensive agents. This response is reported in paper after paper in the dental literature. So now that we've seen that it is difficult to bond to dentin because the systems respond to the acidic properties of our adhesive systems, we need to understand this further. Let's look at this defensive process. This important paper in 2006 was the first indication of the root of our problems, the matrix metalloproteinases. They are and they and other natural defensive enzymes are found in the dentin and are responsible for the enzymatic breakdown of our hybrid layer interface. To try to overcome this problem, Pashley and Tay reported in this paper in 2011 that we can increase the durability of resins by simply enveloping all the dentin in a resin used by our adhesives. Simple enough, at least in theory. But as this illustration from 2012 JDR paper shows, there can be various degrees of hybridization from grade 1 to grade 4, with 1 being close to ideal hybridization and 4 being very poor hybridization. The authors of the paper, Dr. Salvatore Saro and Dr. Tim Watson, pictured in this slide, state that the grade 1 and grade 2 would be nice to achieve in vivo. But with conventional adhesive procedures, that is practically impossible. So why can't we consistently get grade 1 and grade 2 hybridization? Water. Water is needed in the hybridization process to prevent the collapse of dentin fibers, which would prevent the resin to be able to penetrate and enable good hybridization to occur. But wait, we always want to eliminate water in bonding. But if we do so, then we don't get good hybridization because of the dentin collagen will collapse. But if water's always present in the dentinal tubules and always flowing outward from the tooth, then we see that the problem develops. Our brilliant colleague, Dr. Umer Daoud, PhD of adhesive dentistry, posted this image and these words in the Dental Biomaterials Science Forum that we participate in. Umer stated so very clearly that dentin bonding involves a form of tissue engineering. That is, the resin monomers replace the mineral, forming a biocomposite bond containing a polymerized resin and dentin collagen, otherwise known as the hybrid layer. The resin-dentin bonding is achieved via self-etch or etch-and-rinse adhesives by infiltrating into the collagenous matrix and dissolving minerals, upwards to a depth of almost 10 microns in the case of etch-and-rinse bonding systems. During hybridization, an attempt is made to engulf the collagen fibril network. The hybrid layer faces limitations, though. The time and methods involved when performing the procedure, which can limit the degree of conversion and the need of water for maintaining the hydration of the collagen network. He finally states that the hydrolytic degradation of the adhesive resin and the collagen matrix due to the presence of water has a detrimental effect on the long-term stability and durability of the adhesive interface, leading to an influx of bacteria and further biodegradation caused by secondary caries. This excess moisture causes phase separation between the hydrophilic and hydrophobic monomers, creating voids within the interface, and may also lead to less monomer conversion. These voids are beautifully illustrated in this image provided by another colleague, Dr. Walter Zanobi, showing this degradation process with this adhesive, Scotch Bond Universal, after 1 year of water immersion. This is what we are facing, failure, and its frequency can occur no matter how precise we are, or how well we isolate, or how well we follow manufacturers' procedures. To add to the complexity of dentin adhesive bonding, this Journal Dental Research February 2015 paper by Mazzoni, Pashley, Tay et al., entitled The Role of Dentin MMPs in Caries Progression and Dental Bond Stability, brings out the fact that endogenous enzymes remain entrapped within the hybrid layer during the resin infiltration process, and the acidic bonding agents themselves, irrespective of whether they are etch and rinse or self-etch, can activate these endogenous protease proforms. This zymograph article by Annalisa Mazzoni et al. Illustrates the enzymatic response to hybridization. Essentially, in my opinion, the tooth does not like hybridization. Dr. Arzu Tesvergil-Mutlue has published numerous articles on the challenges. Dr. Arzu Tesvergil-Mutlue has published numerous articles on the challenges of our dental adhesives, and having the opportunity to meet and visit her lab at the University of Turku, Finland, was a great honor and pleasure. This article illustrates many of the attempts being made to overcome the durability challenges of our adhesive systems. And she says that the current research in this field, aiming to increase the durability of resin dentin bonds by inhibiting of the collagenylytic activity of dentin, as well as implementing bond strategies which allow the use of more hydrophobic bonding agents, is certainly needed. So let's look at some of the potential agents that are being investigated. Now, chlorhexidine 2% has been suggested for use and used extensively over the course of time, but its bonding is largely electrostatic and has been shown to be not very long-lasting. Benzalkonium chloride, BaC, at 0.5%, has also been advocated and has been shown to tie up a lot of different MMPs, but it's not strong enough against the matrix-bound dentin MMPs. MDPB is another agent that has been suggested, and as it is stated, has been in clinical use for years as a strong antibacterial, but also loses its benefit over time. Crosslinkers are under major investigation by Arzu and her graduate students. Glutaraldehyde and carbodiamide are two being investigated along with the natural crosslinkers such as the proanthocyanidins, a class of polyphenols found in a variety of plants, including grapeseed extract, which is a natural crosslinker. I've personally never been a big fan of glutaraldehyde since, according to my understanding, it is quite cytotoxic. But the carbodiamides are interesting to me in that they are used to activate carboxylic acid, which have been shown to inactivate MMPs. The natural crosslinkers are interesting for what they can do, but they are not aesthetic when used and also require additional steps to use them with our current systems. Ethanol has been proposed to eliminate excess water from the bonded interface. But as is stated in the article, despite the promising results at laboratory studies, a recent study comparing laboratory setting and in vivo testing has showed a 31% lower bond strength at the ethanol wet bonding groups, suggesting that even though ethanol wet bonding approach is promising, the technique sensitivity of this approach challenges its use in clinic, and results obtained in laboratory studies may not be a good indicator of clinical performance. Dr. Bart van Merbeek makes this important comment in this paper from 2014. Moreover, the use of MMP inhibitors applied separately or mixed with primer and adhesives appeared to retard rather than prevent bond degradation. Now, of course, there are many factors that come into play in our composite failures, many of which are listed here, including light energy, correct placement of the light, cavity configuration, opacity of the material, the resin monomer, but perhaps the biggest factor is the human factor. This recent article indicates another problem with our materials. the lack of buffering, which it causes higher susceptibility of composites to our secondary caries dilemma. The data in this article emphasizes further our problems and states that acids in the oral biofilm will negatively affect the bond strength of self-etch adhesives. And interestingly, another published paper by another Pashley and Tay group has this very provocative title, which is Bonding of Universal Adhesives to Dentin, Old Wine in New Bottles. And it concludes, the increase in versatility of universal adhesives is not accompanied by technological advances for overcoming the challenges associated with previous generations of adhesive. Therapeutic adhesives with bioprotective and biopromoting effects are still lacking in commercialized adhesives. Which leads us to a word that is growing in interest in our field every day: bioactivity. What is bioactivity? Well, the concept of bioactive materials was first introduced in 1969, and it was later defined as a bioactive material being one that elicits a specific biologic response at the interface of the material, which results in the formation of a bond between tissue and material. The concept has been further developed in recent years by Jeffries. A bioactive material is one that forms a surface layer of an apatite-like material in the presence of saliva or saliva substitute. So why are bioactive materials important for you and your patients? Well, they deliver minerals beneficial to the tooth. The minerals facilitate conditions that stimulate mineralization and formation of chemical bonds that help to seal the tooth and prevent microleakage. This ionic activity is beneficial for the tooth and the surrounding tissue. Bioactive materials are active, not passive, and play a dynamic role in the oral environment, and they perform favorably in moist oral environment. Bioactive materials can reduce sensitivity. They can reduce marginal leakage and marginal caries, and they can be less technique sensitive. Now, this paper by Stephen Jeffries is the basis of the new definition of bioactivity. It illustrates the apatite crystal formation of the calcium aluminates and the calcium silicates, both known bioactive apatite-forming materials. Now, I had the great pleasure to meet and have my thoughts challenged by Dr. Josette Camilleri while I was in Finland. She is a world-renowned authority on MTA and Portland cements. She states that in a world environment where Portland cements are used, there can be various effects on these cements by the environment in which they are exposed, and all can be destructive to the material. So she asked, what happens to these types of materials when they are used in the oral cavity, which, as she states, is a hostile environment? How do these materials work when they are in contact with blood, tooth, and other agents and materials? We know how they work on the lab bench, but do they react the same way in the mouth? She illustrated during presentation that they very often do not react as expected when exposed to blood and other factors. She said, just because material forms crystal doesn't mean it's doing what you think. What is the material contributing? What is happening to the material, she added. And finally, she says, your material is changing, and change is expected, but may not be as predictable as you expect. Very powerful words. Now, this paper in 2014 reiterates her thought process. It states the hydration and activity of the materials in vivo may not be similar to those displayed in vitro because of insufficient fluid available in contact with dentin. She also illustrated in this paper that biodentine, and she compared biodentine and Theracal LC, that biodentine had the capability of forming the calcium hydroxide, but the Theracal LC was incomplete because of limited moisture diffusion through the material. So again, these are important things to consider. Although they may create crystal on the lab bench, they may not necessarily create crystal in the mouth. This leads us to the term biomineralization. This occurs when the tooth structure is provided with the bioactive materials we have just been discussing, namely calcium and phosphates, and which Jeffrey showed to create apatite, which stimulates mineralization and healing of the tooth. Lena Hoppe in Finland talked about Stephen Mann and his description of biomineralization. In Stephen Mann's papers, he states biomineralization is how living organisms secrete inorganic materials in an organized manner. The formation, structure, and properties of inorganic solids deposited in biologic systems. It is selective extraction and uptake of elements from the local environment and how they're incorporated into functional structures under strict biologic control. Biomineralization, formations of biologic apatite in a biologically controlled process, and it produces a mineral that has specific biologic functions and structures. Now, as I was doing some research, I found this paper by Hench and Greenspan published in 2013 on bioactive glass, which is another very big interest of mine, and collagen interaction. And it pointed out something that was very interesting when I read it. It talks about this gap in the collagen fibrils. The gaps happen to be about 40 nanomicrons, which seem to be the ability for it at those sites to create nucleation for the deposition of crystals of the hydroxyapatite mineral component, which was very interesting, especially in light of this seminal paper by Dr. Salvatore Sardo and David Pashley. In my opinion, this paper is groundbreaking and expands on Jeffrey's work. Now, in Jeffrey's work, he showed that the presence of calcium phosphates could close the gap for the purposes of his experiments. In this paper, Sardo and Pashley enlighten us further with this remarkable statement that the calcium phosphate crystals needed for dentin to remineralize can not be larger than 40 nanomicrons, or they may not fit into the demineralized collagen. And even more interesting, they state that an amorphous calcium phosphate is what is needed to enter into the collagen in a biomimetically stabilized fluid state. Wow! This concept could change everything that we have known previously, and in my opinion is truly revolutionary. Now, Salvatore explained to me this very interesting concept that if the crystals are too large, they're kind of being like Parmesan cheese on pasta. Looks and tastes good, but it really doesn't fit into the sauce like syrup does on pancakes. It sits on the pancake at first, but over the time, it will seep into the pancake and become part of it. This concept is leading us to circumstances of apatite formation and remineralization of the tooth structure in such a way as not really seen to date. This Pashley and Tegru paper illustrates this very nicely. We're seeing work being done to enable our restorative materials to reform and really regrow tooth structure in a fundamental basis, coating the tooth structure with ions and minerals in a form that it can use, which are then absorbed into damaged structure to enable collagen to regrow. This paper in Crystal Engineering and Communication 2014, entitled Remineralization of dentin collagen by metastabilized amorphous calcium phosphate shows step by step how in vivo collagen can be remineralized via the amorphous calcium phosphate. Note the growth and enhancement of the collagen fibers from image A on the left through image D on the right. Fascinating, isn't it? This 2015 paper, published by yet another Tay and Pashley group, shows how in 2 days the calcium phosphate clusters that formed on the collagen fibers can be absorbed into the collagen and begin a remineralization process. We're certainly advancing away from hybridization and toward biomineralization. A few days ago, this paper was shared on the Dental Biomaterials Science and Research Group Facebook page and led to the following statement by Salvatore. The most important problem related to dental fillings in demineralized tissue is the lack of a therapeutic biomineralization. The most important problem related to dental fillings and demineralized dental tissues, Salvatore says, is the lack of therapeutic bioremineralization, which can extend the durability of the resin-dentin bonding interface. Glass ionomer cements, my first love in dental materials, do not remineralize the partially demineralized caries-affected dentin effectively. They, along with most of the restorative materials currently used in minimally invasive dentistry, do not induce nucleation of new hydroxyapatite crystals within the demineralized dentin collagen at the intrafibular level. Salvatore stated that the most important problem related to dental fillings in demineralized dental tissue is the lack of therapeutic bioremineralization, which can extend the durability of the resin-dentin bonding interface. Glass ionomer cements, my very first love in dental materials, do not bioremineralize the partially demineralized caries-affected dentin effectively. They, along with most of the restorative materials currently used in minimally invasive dentistry, do not induce nucleation or new hydroxyapatite crystals within the demineralized dentin collagen at the intrafibular level. New research projects are now focused on the use of phosphoproteins, biomimetic analogs, in combination with experimental bioactive resin-based dental adhesives to remineralize the mineral-depleted dentin so that remineralization of collagen fibrils through precipitation of hydroxyapatite and can restore the elastic modulus and hardness, essentially repairing our teeth. In my opinion, what we've been looking for is currently available in a commercialized product. Current clinical applications in my practice have involved the inclusion of this product, Activa Bioactive Materials, their base liner, their restorative material, and their cement into my practice. When I first saw this product, which was shared with me over 4 years ago, I was very intrigued by what I was reviewing. It seemed like the material could be the best of all worlds in the treatment for my patients. The science presented to me at the time was very exciting, and as I work with this material, I'm continuing to learn more and more about what it can do. So let's look at some of the information and data that I've accumulated on it. First of all, the material does not create a hybrid layer as we are used to in our conventional materials. It creates instead an ionic interface with the tooth structure, not unlike that which is formed initially by glass ionomer materials. However, unlike GICs, this material releases calcium and phosphates, which, as we have seen from Jeffrey's work and as Sarah has previously stated, is important for apatite formation, as such, there is no MMP or enzymatic reaction. Both of these aspects to me are very important. Here's a point you will want to take note of when using the material. and light curing it, which is you're able to light cure it, also self cures and dual cures. So you'll want the material to remain on the exposed dentin surface for approximately 20 seconds to enable the resin in Activa to form a really, really good union and give it full effect with the dentin and the enamel interfaces before you cure. Since the material application can be both light cured or self cured or dual cured, the length of time I just stated when you're using it in self curing mode is moot, so don't worry about that. If you're using a traditional adhesive with the material, which is something that I currently do, wait similarly 20 seconds after applying the material and before curing it on top of your adhesive. I do this as a belt and suspenders approach currently. I want to enable the initial bond strength of our regular adhesives to enable retentive capability and improve the overall ability of the material to stick. But the interesting part is as the enzymes in the adhesives are attacked, the enzymes attack the adhesives, the calcium and phosphate release from Activa will penetrate through the adhesive and form apatite, stopping the enzymatic attack further and ionically forming a great union with the tooth structure. And we'll look at an SEM in a couple of moments. An additional feature which is very unique to the Activa material is the inclusion of a rubberized urethane component, which provides remarkable toughness and durability of the material. It absorbs and dissipates the chewing forces and resists fracture. I've not encountered sensitivity in all of the thousands of clinical restorations that I've placed over the last 4 years and while using this material. We cannot stress enough about how important the formation of apatite is for the best long-term outcomes for all restorations. And this SEM shows the apatite formation with Activa 21 days stored in saline. In fact, the company has SEMs that show how it penetrates through all adhesives that are currently available. So this ability to occlude the gaps and seal the gingival margin against micro leakage is an important goal, in my opinion, as we've been talking about, for long-term success. And here is the edex of the apatite that was formed for those of you who understand this a lot better than I do. So you can use that to compare and contrast. Franklin Garcia Godoy presented this poster at AADR last year and shows the tubular integration and apatite formation of the apatite with Activa baseliner and Activa restorative material. So there's something going on with this material, and I believe that this is a new generation and revolution that's going on. The University of Oregon, again, those marginal failure and demineralization studies also included Activa in the process, and it shows that the Activa material under the same test results shows high integrity and with no marginal leakage, demineralization, or failure when compared to the other materials tested. And again, this should be very interesting to everybody as you work with and review and work on finding out more about this material. Now, my good friend David Clark is an engineering genius, in my opinion. No one has done more work on cavity preparation design since G.V. Black. David's approach to cavity design has led to this calla lily design on posterior tooth preparation. In my opinion, it incorporates more enamel rods into the final preparation and thus enhances the strength of the restoration. I have adopted this concept and used it in all of my preparations. Let's look at a case incorporating this design concept and Activa. Back in October of 2012, this patient presented with a failing DO amalgam on tooth number 5. Note the mesial marginal fracture that's also going on. We wanted to make sure that we could preserve this buccal and lingual cusp structure, so we prepared the tooth in the design fashion that David Clark illustrates, creating this calla lily cavo surface margin that enables us to get more protection to the buccal and lingual cusps. The area was excavated and restored using Activa restorative material. Now, in the preparation and in restoration of and my use of Activa, I will selectively etch all of the exposed enamel and then wash that away after about 10 or 15 seconds. I will then apply a self-etch adhesive to all of the surfaces that I'm going to be restoring for 20 seconds, scrubbing it in with 2 different layers as directed by the manufacturer. I will then place my matrix band around it if I haven't already done that, and then I will restore the tooth with Activa Bioactive. I will either do that in a layered situation, 2 millimeters to 4 millimeters at a time, or I'll sometimes bulk fill the entire preparation. I found that it works quite nicely in both formats. 2 years later, the patient, of course, has been returning for routine dental recare and evaluation. And in 2 years, we've seen that there's absolutely no failure of the restoration. The margins are quite nicely intact. There's no staining. There's no pulling away. At 37 months and at 40 months, we see that the restoration is still surviving quite well in use against the opposing teeth. And of course, now we're approaching 4 years with the use of this material clinically. I have found it to be extraordinarily valuable in all that I do and all of my patients. I have continued to see no chipping, no pulling, no staining, no removal of the restoration from the natural tooth. It seems to be quite nicely in union with the tooth structure. Each day in my clinical practice, I push the envelope to see what Activa can do. And thus far, I have not been disappointed. I want to thank Mr. Larry Clark for the next series of slides, which will help to explain a bit about how Activa is activated. Activa's bioactive resin contains acidic monomers that react with the biofillers and substrates, such as enamel, dentin, zirconia, etc. This resin also contains a rubberized urethane for toughness and is able to resist chipping and breaking while also absorbing shock, thereby protecting the pulp and the tooth from normal everyday function. The bioactive fillers contain and release calcium, phosphate, and fluoride ions when reacted with the acid. These fillers are rechargeable over and over. An acid reaction must occur for ions of the filler to be released. So as the A and B sides of the dual barrel syringes are dispensed in the mixing tip, the acid reaction is taking place to ignite the fillers and prepare the substrate for ionic bonding and sealing. When the acid reacts with the fillers, similar to how this ice reacts with the hot water, ions are released, and at the same time, the fillers and the resin become one. When Activa is either light cured or chemically cured, the fillers and the resin become one. This gives Activa a very homogeneous composition. In combination with the rubberized urethane, the total product can resist chipping, cracking, and absorb shock, similar to dentin. I would recommend that you go to pulpdent.com to download the white paper on Activa bioactive materials. In there you will find over 35 studies that have been published on this material to date. It's an interesting read. In conclusion, I would state that bioactive and biomineralizing restorative materials are the answer that we've been looking for to overcome bond failure. Since when we use these materials as we've described here, when the bond fails, these materials will provide the calcium and phosphate and ions required to heal and regrow structure, form apatite, fill the gaps that may be present, and will also help reduce and potentially eliminate further enzymatic breakdown in our restorations and help to heal and seal the tooth. I want to thank you for sharing this time with me. If you would like to contact me after this presentation, please don't hesitate to email me at jcomisi@jcomisi.com. That's my first initial and last name.com twice. jcomisi@jcomisi.com. Please include the title of this course in the subject line so I can find your email in the various spam that may accumulate in my email folder. Again, I want to thank you for being with me today. God bless and stay well.